All right, thank you. And thank you everyone for being here. So it's really exciting to be here and tell you about the work we're doing in data-driven dynamical systems modeling and control. And so there is going to be a pretty heavy element of fluid mechanics in this talk, but I want to talk a little bit more broadly about sensing, control, and dynamical systems modeling with machine learning. So before I go on, I want to acknowledge my many colleagues, co-authors, and collaborators on this work. So a lot of the data-driven discovery work is with Nathan Kutz, and a lot of the fluid mechanics work is with Jean-Christophe Loiseau. And it's actually a treat. JC is here in the audience, and he's giving the second talk. So this is our first chance to give back-to-back talks about modeling fluids with machine learning. And then a lot of the work I'm going to show has been done by various postdocs and grad students over the years. Okay, so just quick show of hands. How many of you have actually seen this movie before? I play this a fair amount. Okay, so I love this video. I find it to be an incredible inspiration for the work that we do on learning in complex systems. Okay, so we are all here because of machine learning and the ability to discover governing laws or dynamical systems or controllers purely from data. But I think that a lot of the inspiration from this does come from biology, which are expert learning systems, expert control systems, and have an incredible grasp of both modeling, predicting, and interacting with the physical and natural world. So a few features I want to point out about this eagle. You can see this eagle interacting with an extremely complex, unsteady, turbulent gust field. Petros talked a lot about the challenges of modeling fluids yesterday. And I would argue that this eagle, although it looks like it's effortlessly interacting with this environment, this is far, far beyond our current engineering ability to predict and model at all scales. So maybe we could take a box of fluid and discretize it and simulate this with 1 million or 1 billion ordinary differential equations for a few seconds. But that leaves out a lot of the complexity of the feathers and the wings, the compliant surface, the musculature, let alone the kind of neuromechanical control system that's going on inside of this eagle's brain. Okay, and so this is truly a vast and multi-scale system, and I think there's a number of things I want to point out about the inspiration we take from this eagle. So, for example, I don't think the eagle needs to simulate all of those millions or billions of degrees of freedom, because there are dominant patterns that exist for the eagle's daily life. There are patterns of vorticity and fluid mechanics over its wings that are required for it to maintain lift and drag and turn effectively and efficiently. And the existence of those few patterns facilitates low-dimensional reduced order modeling and sensing and control. So it doesn't need to be running supercomputers in the background necessarily. Okay? And it's worth pointing out that this eagle does not have full three-dimensional velocity field measurements, does not have a PhD in fluid mechanics. It probably doesn't even know about the Navier-Stokes equations. It has its experience of itself and its ancestors. It has a pretty incredible sensing system, both in terms of its feathers, its visual system, and various other sensing modalities. But again, its goals are not to do full DNS predictions. Its goals are to effortlessly and efficiently control in its fluid environment. Okay, so a few of the themes of what my group works on and what I'm going to talk about in this talk is that often in complex systems, so I'm going to talk a lot about fluid mechanics, but this applies much more generally to lots of complex systems that we're all interested in. Equations are often either unknown in modern systems or too complex to model. So if you think about neuroscience or climate science, disease modeling, we don't have fundamental governing equations for these systems, or we can't agree on them. Even in Navier-Stokes fluid mechanics, the equations are kind of one size fits all. They're too complex to be readily used for optimization, prediction, and control in real time. It's a one-size-fits-all model. And so we want tailored reduced order models, for example, for specifically the relevant flow structures over a wing. So we can do fast, effective control like the eagle. Another key challenge that motivates us is nonlinear and high-dimensional dynamics. So most of the systems we're interested in have nonlinearity, and they're high-dimensional, either in space or in time or in both. And those really do challenge our ability to interact with these systems, to design, to optimize, and to control. And so a lot of what we work on is discovering coordinate transformations that linearize these dynamical systems or make them simpler in some way. And so I want to point out most of the great breakthroughs in mathematical physics over the last centuries have focused on coordinate transformations and coordinate discovery. Okay? So if you think about the Fourier transform, Fourier didn't cook up this Fourier transform for fun. He did it to linearize the heat equation, to diagonalize the heat equation into eigenvector coordinates, into a coordinate system where things became simple, in that case being sparse and diagonal. And increasingly, with machine learning, we're able to learn these coordinate transformations, these effective coordinate systems where things become simpler. Okay. And so the perspective that we take is essentially to learn physics from data, putting a premium on models that are both interpretable and generalizable. So I don't want kind of big black box models that have 1,000,000 degrees of freedom if I can get away with a model that has 3 or 4 or 5 degrees of freedom, because then I can communicate it, analyze it, and interpret it. And even more, I want those models, because I'm thinking about control as my ultimate goal, I want to make sure that my models are as general, as far away from my training data as possible. Okay? And so if you think about Newton's F equals ma, that's essentially the ultimate generalizable model. Right? It works, you learn it watching an apple fall from a tree. It still works when you launch a rocket to put people on the moon. Okay? So you want generalizability if you're going to do control and modify your system. Okay, good. So this is kind of the framing for the entire talk. I like to put the whole world in one of these 2 boxes, okay? So everything I care about is a dynamical system, pretty much everything. And what we want to do is measure and affect that system with sensors and actuators, and we want to develop some control logic to effectively manipulate the behavior of this system to some engineering outcome. So a lot of what I'm going to talk about in this talk is essentially using machine learning to learn the dynamical systems directly, to model the system. We can also effectively learn the controller without resorting to learning a model. Okay? And in fact, I think this is a really important point for fluid flow control, and it's something that Petros also brought up, is that often if you spend all of your effort up here modeling your fluid system, the first thing you do when you turn on your controller, if you did a good job, is you drive your system away from the region you trained on. And so your model might not actually be that good. And so there's a lot of work developing effective control laws using machine learning optimization. So I'm going to talk a little bit about that right now. And in fact, I'm going to talk about kind of 3 flavors of control modeling using machine learning. The first one is going to be work with Brunton on essentially turbulence control. Okay, and I want to point out at the outset that the way I see machine learning is very simple. I see machine learning as a collection of advanced optimization and regression techniques to build models from data. Okay? And if you think about it, almost every task in engineering and in fluid dynamics is an optimization problem at the end of the day. Reduced order modeling is trying to find the best model, that's optimization, given some dimensionality and given some data. Control is trying to find the best intervention strategy to manipulate the system under some cost function. Sensor and actuator placement are optimization problems. Okay? So flow control is also an optimization. It's a really nonlinear, non-convex, high-dimensional optimization problem, and that makes it challenging and interesting. Okay? So one of the things that Bernd Nowak did a few years ago with collaborators is build this beautiful wind tunnel mixing layer where he can essentially mix up a fluid. So you have a fast fluid dynamic fluid flow on top and a slow fluid flow on the bottom, separated by this metal splitter plate. And you get this nice Kelvin-Helmholtz roll up, and eventually it breaks down until turbulence. And so one thing you might want to do is you might want to measure your flow at some downstream location, for example, using these hot wire rake. And you might want to affect upstream, so this metal plate that separates the flow has 96 independently actuatable pressure ports. You can blow air out of these things up to 500 hertz independently. And so you might want to take these measurements and then do some kind of blowing on the flow to change the profile downstream, to either increase the mixing or decrease the mixing. And if you could do this here, you could translate this to, for example, airplane wings or chemical mixing applications. And so one of the techniques that Bernd and colleagues approach this with is using genetic programming to learn effective control laws from trial and error. So it turns out that simulating this flow is actually quite challenging, and it actually only gets harder when you simulate full aircraft and automobiles. But it's relatively easy to test a control law in an experiment. In about 10 or 20 seconds of an experimental trial, you get a pretty good idea of if this control law, so the control input u as a function of sensors and constants, you can tell if it's good or not in about 10 or 20 seconds. Okay, you can tell if the mixing went up or went down. And so what you do is you essentially run 100 or 1,000 randomly selected controllers. You try them all, and you rank them. You take your best performers, and then you run through these genetic operations, mutations, crossovers, things like that, to breed successively better generations of control laws that are more effective at minimizing your cost function. Okay? And this is pretty effective in a number of turbulent fluid flows. So you can get about 20% better mixing enhancement. You can get drag reduction in other experiments. So I thought that was pretty cool, just using genetic programming. So another application we look a lot at is renewable energy in offshore or river-generated hydropower. So this is what we call a cross-flow turbine. Cross-flow just means it's a vertical axis turbine if you knocked it over and put it in a river. Okay, so it wouldn't make sense to call it vertical axis if it's on its side in a river. And we have a lab-scale version of this that's about yay big in a water channel at University of Washington. And so Ben Strom, who is an excellent PhD student with Brian Pelagi and me, wanted to maximize the power of these cross-flow turbines for renewable energy in remote sites. Now, what you would do in a helicopter that had rotating blades is you would dynamically pitch these blades at different phases of advance and retreat as it goes around in its circular loop. But because this is in a remote village in Alaska, you don't want to have any moving parts, because you can never fix this thing. You don't want any maintenance costs. You don't want this thing to break down every 100 hours like a helicopter does. And so what Ben realized is that instead of dynamically pitching the blades, because this thing is moving around in a circle, you can optimize the acceleration and deceleration profile. You can essentially accelerate into certain parts of the turn and decelerate into other parts of the turn. And it gives the effect of the blade pitching up and pitching down in its reference frame. Very cool. And so this becomes, again, a high-dimensional optimization problem. We're essentially trying to optimize this blade acceleration profile as a function of its phase angle to give the maximum power output possible. And so Ben essentially tried various optimization strategies and was able to find a very, very effective one that gives about 60% power increase over industry standard control in our lab experiment. And the thing I think is really cool about this is that the procedure, we didn't put any physics in at all. We essentially just wrapped an optimization loop around the experiment. And it learned that for certain profiles, you can create this large leading edge suction vortex here at the right phase so that it coincides with the power stroke of the turbine. So you get the maximum torque at the maximum velocity, and you get this maximum increase in power. And so here's kind of a movie of this thing going around. You can actually see it forming this large leading edge vortex at the right time, and then it will shed it at a time where it won't affect the downstream blades. This is a two-bladed turbine. Pretty cool, okay? You just have to frame it as an optimization problem with a well-defined cost function. And essentially, this is a plot showing kind of the velocity and torque and the overall resulting increase in power, because you can align them with the control. But the ultimate goal here is not just to have one turbine, it's to have an array of turbines. Okay, so you want to essentially put these things in a dense array packed together, and this is actually exactly like what Petros was showing. You want to use the same principle that fish use when they school to kind of get this favorable interaction of these turbines together. So we need to understand not just how to optimize the power of one turbine but where the wake structures are going and how to place them for the downstream turbine. And so this is actually a teaser for work that Isabel Scherl in my lab is doing right now, is applying these machine learning optimizations to place a second turbine in the wake of this first turbine. These are finite time Lyapunov exponents of the first turbine. And so if you can picture what Petros was showing with the fish yesterday, you essentially want to place the second turbine at a favorable location so that these blades can kind of piggyback on these very, very strong coherent structures generated by the first. And again, this is all experimental data from a lab scale test that we're doing in Washington. Okay, so the third flavor of machine, oh yeah, question.
Surely that's going to vary dependent upon the flow speed, and so it's likely impossible to have an optimal thing with something as fast as
Yeah, so it does depend on flow speed and Reynolds number. It depends on turbine geometry. It depends on a lot of things, absolutely. So it's easier to optimize these in a river than in a tidal basin. So the tidal basin is a little tricky because you have a whole range of velocities, and so you get to decide where to optimize. So there's two things we're trying to do. One is we're trying to understand the fundamental physics and how it scales so that we get a good idea of what would work most of the time. But the other thing we'd like to do is run this optimization loop online so that as the flow speed varies, or if there's a disturbance, or if a rock moves and starts creating vortex shedding, we can kind of adaptively correct for that on the order of minutes, which we think is pretty feasible based on what we've seen in the lab. Okay, great question. And please do ask any questions in the middle. Okay, so the third flavor of control is essentially using deep model predictive control for fluid dynamic control. So here we see, this is a recent paper by Katarina Beeker and Sebastian Peitz. And what we see here is a single cylinder, the vortex shedding behind a single cylinder. And this is the new fluidic pinball, which is a really cool name for 3 cylinders in a triangle. Okay, so the 3 cylinders in a triangle, you can independently spin these around, and you can get very different and kind of richer dynamics. So you can have almost turbulent wakes behind this, which are a little bit more complicated than the regular cylinder flow. And so what we're going to do here is we're essentially going to use deep learning to build a predictive model for the evolution of this flow under different control strategies, and then wrap that into a model predictive control loop. Okay? And so this is essentially what you would normally do if you could afford it. You'd have the full model, the full DNS simulation. In real time, you'd be predicting the control output, but this is far, far too expensive. So instead, what we do is we use this surrogate model, and we're going to learn this essentially using a deep neural network, and then wrap this control around the simulated system. And so when you do this, here, these are the commanded lifts in dashed for the 3 cylinders. So we make one of them have a high lift, one of them have a low lift, and one of them have 0 lift. And you can actually see that our actual system is doing a pretty good job. There's a little bit of ripple from the vortex shedding, but more or less we're able to control this system to our reference lifts pretty effectively. One thing I thought was really cool, though, is that our architecture is actually online trainable. So what you can do is, as you apply this control law, you can retune your neural network prediction to characterize that new attractor. And if you retrain in time as you go along, your control cost goes down and your mean error goes significantly down. And you can see that we're actually getting a much, much better tracking of our reference lifts if we do adaptive learning of our neural network model as we go. Okay, so that's kind of neat. Okay, good. So I've talked a lot about fluid dynamic control.
Was that simulation, or was that a lab?
That was a simulation. Yeah, we don't have that experiment yet. Okay, so I talked a lot about control. But the first step in control, generally, is picking sensors and actuators, actually picking the hardware that you're going to use to control your system. So we also spend a lot of time thinking about how we can use these kind of high-dimensional, nonlinear, non-convex optimization techniques to learn effective sensor and actuator placements so that we can do good control in the future. Okay? Here's just a cool schematic I like of, if you had some library of behaviors, how would you sense that system effectively to tell what behavior you're looking at? And I want to go back to the bio-inspired perspective. So this is work that I do with Bing. She has a MURI to study insect flight dynamics and control using sparse sensing, which I think is really, really interesting. And I want to just take a little bit of an aside to tell you about how we think about insect flight and how it kind of informs some of the work we do. So I showed the video of the eagle on the first slide. It's a kind of amazing demonstration of real-time flow control. But insects also interact with very complex turbulent fluid environments, and to some extent I find this even more impressive, because the eagle actually does have pretty sophisticated computational hardware. It has lots and lots of sensors. It's a very sophisticated animal. The moth, less so. But the moth is also able to navigate these extremely complex turbulent gust fields and plumes. So a couple of interesting facts about the moth I want to tell you about, things I didn't know until working with biologists. Every single flying insect, all of them, have on the order of tens to hundreds of strain-sensitive neurons on their wings. All of them. There are these little strain-sensitive neurons, campaniform sensilla, that are distributed in a pretty regular pattern on the wings of all insects, and they use these to inform their flight dynamic control system, to measure forces and accelerations and things that are happening, disturbances, and they use these for very fast, effective control. So another thing that's really interesting is that if you hit a moth with a gust, you can do these really cool experiments where a moth is flying and you whack it with a gust. The moth can correct its flight pattern, its wing beat frequency, faster than that information can go to its brain and back to its muscles. That's remarkable. And so what's happening, we believe, is that the insect is assimilating this sensor information into a local computation in its shoulder muscle, and it's using that information directly to affect its control system, its muscle control for its flight. And so this is what Bing calls proof by existence, that you can get away with sparse sensing and very low dimensional computations for an extremely sophisticated control system. Pretty amazing. So we've been studying this as long as our daughter has been alive, so a long time, trying to understand how this insect why it would place its sensors here, how it would process the information, and how it would use it for effective real-time control. And so we've back-engineered a lot of this technology, and I just want to point out, if you're interested in sensors, if you're interested in compressed sensing or sparsity, there's a lot of cool applications in engineering systems that you can use. So once you kind of back-engineer how these sensors could be used to inform either classification tasks or estimation tasks or control tasks, again, it's an optimization problem to figure out where you would put these sensors. You can use that same technology to design sensors to help Boeing, either in its manufacturing or in its flight dynamic systems, to place sparse sensors in the ocean to estimate flow field temperature, or for input-output control systems. And so these are all applications Krithika Manohar worked on when she was a PhD student. And then this is work by Tomas and Bing in actually understanding kind of the insect. Okay, so I've hopefully convinced you that machine learning can fit in lots and lots of different aspects of this control loop. For the remainder of the time, I'm going to spend my time up here. This is kind of my passion, is using data-driven modeling to get reduced order models of complex dynamical systems. Okay? And I want to point out that there is a ton of great work on this field. I mean, this is 1% of the work. I'm actually highlighting this specifically because this work in the last 10 years on model discovery has really taken a change in perspective from classical system identification of the 80s and the 90s to really put a premium on parsimony and sparsity in the model. Okay, I don't want the best fit model. I want the best fit model with the least complexity. Okay, and it's obvious, I think, when you say it. but that's a relatively recent trend in data-driven modeling. I would say major work in the last 10 years, okay? And so that's what I'm going to talk about for the rest of my time. Okay, so I'm going to walk you through the sparse identification of nonlinear dynamics, the SINDY algorithm here for obtaining nonlinear dynamical systems models from data. And then I'm going to show you how we're using this to model interesting complex systems in fluid dynamics and other fields. Okay? Okay, good. So I'm going to illustrate this on the Lorentz system, which I think is a pretty simple, simple toy system. You have 3 states, x, y, and z, and you have simple quadratic nonlinear dynamics. Now, I really want to point out and emphasize that the right-hand side here is very simple. In fact, the right-hand side of most of your models, your textbook models in physics, are simple. Out of all of the possible right-hand sides of all the complex models you could have, most of the things we observe actually have only a few terms. Various reasons for this. You could argue that it's a Taylor series expansion of the real physics. You could argue that it's asymptotics. But it's an observation we made that most models are very simple. And when I say simple, I think of sparse. There's only a few terms here out of the possible terms. So the way that we work this algorithm, assume you have data x, y, and z of your state in time. So each column is a time series of data. And assume that you have the derivatives x dot, y dot, and z dot in time. Now that's a lot of assumption. Generally, you don't have full state measurements and full derivatives. We're going to relax that in a little bit, but it's easier to illustrate assuming you have all of the data. How many of you have heard of dynamic mode decomposition? Okay, most of you have heard of DMD. So what DMD would give is a little 3x3 linear model right here. Okay, we give the best fit linear regression model that fits x dots given x's. It would be a 3x3 linear model. But we know that that's insufficient to handle truly nonlinear dynamics on a chaotic attractor. So instead what we do is we build an augmented library of possible candidate terms that could be in our right-hand side dynamics. Okay? In this case, polynomials up to 5th order. And each of these gray columns, importantly, can be computed from the data. I can take the data x and I can square it or cube it or multiply it by y. And I can build this whole library. And now, if you write the dynamics in this library, each of these x dot, y dot, and z dot terms is essentially a sparse combination given by these coefficients c of these library elements in theta. Okay, and so the inverse problem is essentially to try to find which of these columns, which small subset of these columns adds up to explain x dot, y dot, and z dot. Okay? Now, if I had posed that problem 20 years ago, it would be unsolvable. It would have been a combinatorially hard brute force search through all possible models with 2 terms and 3 terms and 4 terms. Now it's a relatively straightforward sparse regression problem. There's many, many techniques. There's a wide range of techniques to solve this sparse regression problem to find with high probability the fewest columns of theta that describe x dot, that describe y dot, and that describe z dot. And when you apply these techniques, what you do is you simultaneously find the structure of which nonlinear terms are active and the coefficients for those model terms. Okay, so you can actually discover nonlinear dynamical systems purely from measurement data using this method. Now, there's a lot of assumptions here, right? I assumed, for example, that I had the right measurements x, y, and z and their derivatives. That's the big first assumption. I measured the right thing. The second big assumption is that I can build the right library where the dynamics become sparse. Polynomials tend to work for lots of systems, especially fluids, but you could have built in sines and cosines and Bessel's functions, whatever you want. And then the third assumption is that I can actually solve the sparse regression problem to find the fewest terms that are active in my dynamics. Turns out that third one is the easy one. Sparse regression is the easy part. Getting the right measurements and getting the right library is typically much harder. Okay, so I'm going to start relaxing these various assumptions. I assumed I measured x, y, and z and the derivatives. Now let's start systematically relaxing those and applying this to harder problems. Okay? So the first thing you can do is you can get rid of the assumption of measuring the derivatives, and we can instead just measure collect noisy measurements of the state x, y, and z. So these are my actual measurements here, this kind of fuzzy attractor. And what you can use is total variation regularized differentiation to approximate the derivative of x, y, and z. And when you plug these approximated derivatives into the Cindy algorithm, you find you actually get the right structure of your model. And almost all of the coefficients are pretty accurately preserved, except this one's off by about 20%. Interesting. We're minimizing total variation. And I'm really glad Stan is in the audience, because we're actually using this original method that there's your name. So we're actually using the code by Rick Chartrand here, based on the total variation minimization. But I think this is pretty incredible. So you can take really noisy measurements, and this is a testament to, again, total variation regularized derivatives, but you can take very noisy measurements and actually still discover the right structure of the model. You can also extend this to partial differential equation modeling. So instead of ordinary differential equations, you can collect the same high dimensional measurements. And instead of building x dot equals, you can essentially build partial derivatives in some state vector, for example, vorticity, and solve the same sparse regression problem to find the fewest terms that give you the time derivative of omega. And in this case, what you find is a very simple model that matches the Navier-Stokes equations, for example, if you give it fluid data. And here you even get the Reynolds number to within 1%, which I thought was really cool. Okay, this is clean simulation data. You can also do this because there's so much data here. If you take points in space and in time, you can massively subsample your data. I don't know if you can see these little green squares, but you can massively subsample your data in space and time, and you can discover the same partial differential equation. Yes?
Could you reproduce this with the primitive variables instead of vorticity? Write a vector of u?
I think you could also do this with U's. It just is it's a simpler representation here. It's easier to write down and visualize. Yeah, I think this is actually mostly because I like plotting it in vorticity. And so we've essentially used this for rediscovery of partial differential equations we already know, but we're currently working with collaborators to now discover coarse-grained models that we've never seen before, for example, in plasma physics, in fluid mechanics. So there are hierarchies of models of different descriptive ability. Okay, so modeling is always a balance between how accurate you want your model to be and how effective or efficient you want your model to be. And so Navier-Stokes is very, very accurate, pretty slow. And what we're trying to do now is find kind of reduced order models, coarse-grained models that are less accurate but less computationally intensive. So sparse regression essentially means some principled relaxation of an L0 minimization. That's what I mean it as, is I'm trying to solve this regression problem with a sparse vector of coefficients rather than a least squares vector of coefficients. So there's various ways you could relax this. So for example, the lasso is kind of the most obvious approach, would be just relax this to an L1. That doesn't have the best performance. So we have our own homebrew process that is also a formal relaxation of the L0. And in fact, that's actually what I'm going to talk about next. Okay, so I want to take a step back and just think about what we mean by parsimonious modeling in general. Okay, so this is the problem we're trying to solve. We have x dot, we have a library of candidate terms, and we're trying to find the fewest linear combination, the smallest linear combination of those terms that describe the dynamics. And we're doing it by essentially penalizing the zero norm of my coefficient matrix. I want to have as few terms as possible here. So we get to choose how aggressively we penalize sparsity, or number of terms in this model with this lambda parameter. Okay? And essentially what we're going to have is this trade-off between error and complexity. So I'm measuring complexity and how many terms my model has, and error I'm measuring using this to norm or fro norm or whatever you like. Okay, so as I sweep through lambda, I can get very, very simple models or very, very complex models. Let's take the limit of lambda goes to infinity. If lambda is infinity, then that's the ultimate penalization on sparsity, and I basically that basically imposes that I have no terms active in my dynamics. It's so expensive to have a term that I have zero dynamics. Okay, so if lambda is infinity, then I get the model x dot equals 0. Clearly underfit, very high error, very low complexity. Okay? In the other extreme, if I make lambda 0, I'm not penalizing sparsity at all. That's just doing a least squares regression. And if I do a least squares regression here, I'm going to get a coefficient vector that has a little bit of all of the terms active. In this case, there's 81 terms. So I'd have a model with 81 terms in the dynamics. We know that's overfit, right? We know that our physics doesn't probably have 81 terms, but it is going to give me lower error on my training data. Okay? Now what you hope is that there's a whole family of models between these for different values of lambda. And in fact, you hope it looks like this, where there's a Pareto optimal curve. It's also really, really important to test your models on actual test data that's not used to train, because then you can actually see that your least squares solution is incredibly overfit. Okay, those 81 terms might even be unstable if you apply it to a new trajectory. And so what you're really trying to do is sweep through lambda to find this sweet spot where you have just the right amount of terms that is necessary to describe the dynamics accurately and no more. So that's where these kind of parsimonious models live down here in this cross-validated regime. And there's a lot of techniques to do this. A lot of people think about parsimony, and there's a lot of techniques to select these models. So I mentioned that we're not using lasso because the lasso algorithm tends to get stuck in the wrong solution early in the path. So you often either kill the right terms early and you can't get them back, things like that. So what we do is something called sequentially thresholded least squares. Super simple algorithm. It was born out of essentially desperation because we couldn't get compressed sensing to work on this. What you do is you do a least squares solution. You get a little bit of all of these terms, but a lot of them are small. And so you hard threshold those. Then you do another least squares regression onto the remaining terms that are non-zero. Now some of those are small. You kill all of those. And you do this again and again and again until it converges. That's sequential thresholded least squares. And there's variants of it where you can kill one term at a time or multiple terms at a time. But it's very simple. You do a least squares, you kill the small terms, and you do it again until it converges. Now there are some chief benefits of doing it this way. In addition to the fact that it doesn't get stuck as often and it's more robust to noise, it's also based on a least squares regression, which means that you can do lots and lots of other things while you're doing that least squares regression. So we didn't realize this at the time, but actually JC found out that you can impose physical constraints on your model by doing constrained least squares with sequential thresholding. Okay, and so that's what I'm going to talk about in the next section on fluid mechanics. Okay, so we have this tool, Cindy, that can discover toy systems that we already knew the answer to. It's particularly useful if we can use it to solve or to model systems we've never seen a model for before, like this fluidic pinball. So that's what I'm going to tell you about for the rest of the time. So I'm going to look at this fluid flow past a cylinder characterized by Kármán vortex street. This is at Reynolds number 100. And so this fluid flow was a nice test case for Cindy because there's a really interesting about 30-year history of how reduced order models were discovered for this system. And I'm going to tell you a very abridged and partially true, partially complete history of this system to kind of motivate that it's interesting and challenging to get a model for this. So in the 70s, Ruel and Tawkins, the same Tawkins of the Tawkins embedding, time delay embedding, had a hypothesis that the chaotic and rich turbulent dynamics that were observed in fluid flows might be explained through a sequence of Hopf bifurcations as you increase the flow velocity or the flow Reynolds number. As you increase it, you go through one Hopf bifurcation and you get periodic motion like this. If you go increase it more, you go through another Hopf bifurcation and you get quasi-periodic behavior. And if you go through a final Hopf bifurcation, you might get chaotic and turbulent behavior. Okay, that was a hypothesis in the 70s. About 15 years later, numerically, researchers discovered that, in fact, these Hopf bifurcations do exist in fluid systems. But that actually begged more questions than it answered. Because for those of you who know dynamical systems, the Hopf normal form is a cubic nonlinearity. But the Navier-Stokes equations are fundamentally governed by quadratic nonlinearities. The convective term in the Navier-Stokes equation is quadratic, not cubic. And so that begged the question, how could you have a cubic Hopf nonlinearity in a quadratic system? And so it took another 15 years before Bernd Nowak and collaborators explained how you could have this Hopf bifurcation with a quadratic system. And so what he did is essentially write this fluid flow system in a reduced coordinate system given by two POD modes. These are the principal components or singular vectors of the data. And a third mode called the shift mode, which essentially there's an unstable equilibrium here that you would never see in experiments. And the shift mode connects this unstable equilibrium to the average flow if you just average this time series. Okay? And in this coordinate system, he derived this reduced order model here, where the z direction, this z direction here, is much, much faster than the dynamics in the first two POD modes. And so what happens is very rapidly, z equals x squared plus y squared. If I start off of this slow manifold, I very rapidly glom on, where z equals x squared plus y squared. And if you plug that in to the dominant dynamics up here, you get the effect of a cubic nonlinearity, and it looks exactly like the Hopf normal form. So what he discovered was that through this slow, fast separation of timescales, you could get the effect of a cubic nonlinearity in this quadratic system. And so it kind of put a nice close on this 30-year history of Hopf bifurcations in fluid mechanics. So we saw this as a challenging test case for Cindy. We were going to take the exact same coordinate system. Again, I'm assuming I'm measuring the right thing. I'm still using Bernd's coordinate system. We measure these three variables. We plug that into the Cindy algorithm. And what we found was that the identified system actually had the right slow, fast separation of timescales. It had quadratic nonlinearities, and it had this parabolic slow manifold. So it had all of the main features that we were looking for from this model, which was pretty neat, and gave us some confidence that we could actually use this for discovering new models, because this is a real research problem that took people a long time to discover. Yes?
To discover the model, did you only use the data from the asymptotic simulations, meaning only from the pre-algebra?
No. So that's a really, really important point. So actually, there's two different sets of simulations we tried, three. You could just start on the limit cycle, which is the movie I'm showing, and that would not give you this model at all. The simplest model that describes this limit cycle behavior is a linear DMD model, by far the simplest model. Then what you could do is you could start near this unstable equilibrium, and you could watch this thing slowly unwind on the slow manifold. That also didn't work. So in addition to that trajectory, we also started with a trajectory here at the mean flow that goes down and then spirals up. And so you need transients to be able to capture these extra nonlinear terms. Hugely important. Thank you for asking. You absolutely need to have transients in your system, kick the system in some way off of the attractor to really get the dynamics. Okay? So this is where the story gets, I think, pretty interesting for me. We put this paper on the archive, and within a relatively short amount of time, we got an email from JC, and he pointed out a few key issues with our model. So I don't remember exactly all of them, but I think we had the wrong unstable growth rate mu. We had, I think, a spurious fixed point down here for some reason. I think there was a constant term. It wasn't perfect, the model, okay? And we were a little bit despondent. But fortunately, about 2 weeks later, JC emailed back and had completely solved it. And so this is one of my favorite things in this whole Cindy modeling framework is JC's solution to the cylinder problem. So essentially, he came up with two incredibly important ideas for modeling fluid flows with Cindy that we're still using today. The first one is, again, because our sparse regression is built on a sequentially thresholded least squares. We essentially are just doing least squares and then killing terms. It's relatively easy in our least squares regression to add linear constraint equations. Okay, so constrained least squares is approximately as easy as regular least squares. And so there are lots of things we know about the fluid equations, the Navier-Stokes equations. For example, we know how energy is conserved in incompressible Navier-Stokes, or at least JC did at the time. It's because of skew symmetry in the quadratic terms of our model. And you can actually write down what those skew symmetric terms look like for a model with 3 equations, x, y, and z. And you can enforce that the Cindy model has to have those symmetries in the equations through an additional, I think, 8 or 9 constraint equations here. So that's amazing. You can build models that are stable by construction. They're guaranteed to conserve energy. They can't do anything otherwise because it's fundamentally baked into the regression. So that, I think, is a very plausible way of incorporating partial physics knowledge, either in some known symmetry or energy conservation, mass conservation, something like that. The other innovation I think is really cool. When we were developing this model, I was going for a quadratic model because that was the history. The 30-year history was how do you get cubic Hopf with a quadratic model. But if you relax that and you allow yourself to have cubic, quintic, septic, higher order terms in your dynamical system, essentially what you can do is you can account for the energy that you threw away in your principal components. So remember, I'm building this model on the first 2 principal components. Well, there's principal components 3 and 4, and 5 and 6, and 7 and 8, and those have energy too and are important for the dynamics. Those also are faster and faster timescales and substitute back in as higher order nonlinearities in the asymptotic analysis. And so what JC realized is that if you allow yourself to have higher order terms, you're essentially getting a closure model for the effect of those higher frequency, lower energy POD modes that you're truncating. So with fewer terms but higher model order, you can account for all of the energy that you're discarding in that Galerkin system. So I won't say that this is, this is a laminar problem, so it's not turbulence closure, but I think it's highly suggestive that you can use some of these methods in more complex fluids. So very, very exciting. Okay, I have a couple of slides here to show, actually. So this is how you get energy conservation for an incompressible fluid. It's essentially this integral of U dotted into the convective term. This is what it looks like in the reduced order coordinates A1, A2, A3. And these are the equations that JC derived that have to be true. This all has to equal 0. So again, you can do this for pencil and paper for your symmetry. And you arrive at these constraint equations that have to be true for the Cindy model. If this is true, your model preserves energy by construction. Okay? And again, you can then write that as this matrix set of constraints and solve it using KKT constrained least squares. So I want to compare this against classic Galerkin projection, because I think that's, Galerkin projection is the gold standard for reduced order modeling of fluid systems. What you see here in white is a proxy for the drag coefficient, the drag of this cylinder, starting from that unstable equilibrium as it goes into steady state. And this is what the Galerkin model does for 3 modes and 7 modes. Okay? So it gets the right qualitative behavior, but there's a pretty big overshoot. It doesn't have the right steady state, and the growth rate is wrong. And if you plot it in POD coordinates, you can see that it's qualitatively the right dynamics, but it's quantitatively off by quite a bit. But if you include either these constrained or cubic Cindy models, you almost perfectly capture the growth rate, the steady state behavior, and there's no overshoot. So this is really remarkably more accurate. JC also applied this to the cavity flow, and I believe since then to many, many other flows. But you can see that you get qualitatively better models with fewer POD coefficients, okay? And they capture more of the elements. And something I thought was really cool is that when JC rewrote the equations that were discovered out, you can essentially write it as this van der Pol oscillator. So I think to date, this is the simplest model for the cylinder that has been written down that captures all of the transient dynamics. And it's just a van der Pol. It's a nonlinear oscillator with a nonlinear damping coefficient. That describes the cylinder. Something else that's really cool is that you can apply this not just to POD modes of the fluid, but you can apply this to physical measurements like lift and drag. So one of the big problems that we have in fluid mechanics is the things we do in simulations and in the lab don't always translate over to Boeing and Airbus. Right? In the lab or in a simulation, I have this full flow field. And I get to measure the whole thing. I get to compute POD modes. I get these global modes that describe the behavior of my system. But in reality, I don't actually know what my entire wake is because I don't have measurements. What I have measurements of are either on the surface of my wing or maybe some acceleration or lift or drag, something like that. And so what we tried next was essentially on this flow, instead of building Cindy models on POD of the whole wake, it turns out it's possible to build these Cindy models just on the lift coefficients and their derivatives. So if all you had was the lift measurements in time for these 3 cylinders, you can build a nonlinear model that is remarkably accurate in capturing those nonlinear dynamics for this system. Okay? So this also fixes the problem that if you slightly changed this geometry, or if you accelerated the flow to a slightly higher velocity, all of these POD modes would change. But the lift and drag measurements are essentially intrinsic measurements. Those don't change if I change the geometry. So in the past, you couldn't build a Galerkin model for different geometry because your modes would change. It would be apples and oranges. But if you build your model only on lift measurements, it's apples and apples, even if you change your geometry. Okay, so I thought that was pretty remarkable. Okay, it looks like I'm running out of time here, so I think I'm just going to kind of end here with a couple of key themes, just a summary. We spend a lot of time thinking about how to discover models for our systems when we don't have any. Even when we do have them, we still want reduced order models that we can use for prediction, estimation, and control. So think about those last models I showed. Those are far, far simpler than the full Navier-Stokes DNS. Okay? A model in 2 ordinary differential equations is better than a PDE for our purposes. I didn't get to talk too much about how we handle nonlinearity and coordinate transformations. If you're interested, please come talk to me afterwards. And if you have any interesting fluid systems, definitely talk to JC and me. Okay, thank you all.